Okay, thank you, everybody. Well, thanks for Susan for outreach to me and giving me opportunity to talk. And last time when I'm giving the talk to the department was probably 5 years ago, and you know, David and Mark may still remember that. So it seems to me the time flies very fast here. Anyway, I'd like to report some progress that my team has been doing in environmental sensing from space and also in agricultural fields. And I'd like to acknowledge my group members, and you can find the link here since we are in the same university. So I'm not going to choose their pictures or mention more beyond that. Many of you actually know them. So I will just go ahead to start it. I will start with an introduction that many of you know that satellites for Earth observations has two orbits. One is the geostationary orbits, one is um, the lower Earth orbit called and for the geostationary orbit, basically you stare at the Earth and you have the same angular speed as the Earth. Therefore, you can look at the same area constantly at every hour. And these days, you can some of satellite looking at every 5 minutes to monitor the weather, monitor the fire. And then this lower Earth orbit is generally can go somewhere from the International Space Station all the way to somewhere 800 kilometers or even above. And for most of the weather applications, environmental applications, you fly from pole to pole, called polar orbiting satellite. So you get a global coverage once per day. So a bigger picture is that in the past 20 years, this what we call the afternoon satellite constellation, sometimes we call them A-train, is probably the state of the art in terms of our Earth observation capabilities that NASA has put together. And this A-train, the primary time is actually 10 years ago, like 2010. By now, many of which actually already departed from the A-train. But nevertheless, what we learned in the past 20 years is that we know the global and horizontal distribution of atmosphere and land properties very well. The reason we call them a train is because each of those satellites, they are about less than 10 minutes apart in the space, and they align as a train, so you can get measurements of atmosphere and land properties and ocean surface property as well in every day globally at the local time at the 1:30 p.m., but also at the 1:30 a.m. in the morning for those measurements that measuring the radiation in the in infrared wavelengths and microwave wavelengths. So what we don't know well is that how the atmosphere changes with local time and the distributed energy and its composition vertically. We don't know that pretty well because all those satellites that we measure are basically 700 kilometers above the surface. But what we live is really near what we call the planetary boundary layer. And we really want to know what is happening near the surface from like within 3 kilometers above the surface, maybe to about 10 kilometers above the surface. So how do you sense those information that while your satellite is way up in the 700 kilometers above, right? So we want the information close to the surface, but this is a very challenging problem and we don't know them very well. So I'll give you an example here. So this is one of the last year, around almost 1 year ago, exactly 1 year ago. And what you can see here, you can see the fires pretty well. You can see the smoke transport to our area pretty well. But what you don't know is that is the smoke layer near the surface or not? We need this 3D information in real time. And unfortunately, we don't have a passive, we don't have a product so far to tell you that where the smoke is up in the atmosphere or near the surface. So my talk is try to share some progress that we have been making on remote sensing of fires. And we want to get more information about the fires. we also want to get more information about aerosol transport in the vertical. And then going from there, I'm also going to mention a little bit of the low-cost sensing in the rural communities that's the project that we have been doing in collaboration with many of you in the department. And I will share some thoughts for future directions. So first of all, let's do a kind of fun experiment here. So why does a candle blow out, right? You have a birthday party and you blow the candle. And why when you blow the candle that you can see they blew out? So why is that? There are three options here. A, our breeze is mostly CO2, and we know that combustion needs oxygen. So when you blow there, you blow out, it's diminished. B, our breeze is cooler. Maybe that is too hot, so we have cooler air go there and maybe kill them. That decrease the heat, right? C, the wax vapor, the flaming part is moved away. And so which option do you choose? You can probably, I don't know, you can, how do we do this? Susan, how do we do this? You can do a, maybe type in the chat or maybe.
Yeah, let's go ahead and type our answer in the chat.
Yeah, let's do that. I cannot see your answer because I'm doing the full screen here, but you can tell me how many people are selecting A or B or C. I give about 30 seconds to do this.
Looks like everyone is choosing C.
Oh, wow, we have good people. We have good people knows physics well. Great. Well, the answer is C, right? So when you blow out this flaming part, bring a pen here. This flaming part goes to here, right? Somewhere around here. Now you cut off the supply of the fuel from the candle. So therefore, what you get out is that only thing left is hot and it's smoldering here. So similarly for fire is the same. Fire needs three components in order for fire to happen. One is fuel, one is oxygen, and then the third one is heat. And given the, what you have seen in the media and such, the fires is the norm in the Western US every, late summer and early fall. So there are a lot of work has been done to study the fires in terms of their environmental impact. And they are studied by a wide range of the techniques from lab measurements to aircraft to mobile facilities, and certainly using satellite to study that. And so, so in terms of the remote sensing of fires is actually the concept is actually pretty simple because the fire is hot, so your temperature is higher than the surroundings. So if we see a pixel, its temperature is higher than the surroundings, we should be able to detect them, right? So according to the Planck function law, when the temperature increases, the peak, the wavelength at which you have a peak radiation getting shorter. So this is 11 micrometer, and this is 3.7 micrometer. You can see if in our land surface temperature around 300 K, then you got 11 micrometer radiance is larger than your mid IR, shortwave IR radiance. But if you go to 500 K or even larger, when fire to start, you can see the 3.7 micrometer apparent temperature will be larger than 11 micrometer. So we can search at what pixel this radiance in the midwave IR is larger than the thermal IR, and then you find a hotspot. That's the fire. Now through the years, we are able to detect the fires in the cloud-free conditions. We are able to see using the visible techniques to study fire burn area after the fact. After the fires are gone, you see, oh, the canopy NDVI diminished. That's where the fire have a scar there. We can see the fire burn area. We can see the fire radiable power. We can also do some what we call subpixel retrieval to retrieve the fire temperature in the fire area. And we can also get some a little bit of information about the smoke volume height in the source region by using stereo type techniques, stereo imaging technique. But anyway, what we don't know is that how the oxygen and the fuel are interacting. What we know is the heat and the fuel. So we have been trying to push that frontier a little bit, try to retrieve the fire combustion efficiency. How much, to what degree the combustion is completed. So why this is important? Well, in terms of quantify the fire combustion efficiency, we use something called the modified combustion efficiency. Basically, the ratio between CO2 and the CO plus CO2. You would imagine if the fire is completed in the complete combustion, everything goes to CO2, the combustion efficiency goes to 1. But if you are incomplete combustion, you have lots of them goes to carbon monoxide. So this ratio will be less than 1. So notice that in here, those are from field experiment. You can see even as your ratio changing from 0.88 to 0.96, that 0.08 change will lead to a decrease of the organic carbon emissions by a factor of 5. Lead to the increase of the sulfate emissions by a factor of 5. And then lead to the increase of the soot particles, right? These are the element carbon to the organic carbon. Those particles are by a factor of 5 as well. So even it's tiny bit of a change of the combustion efficiency, you have a bigger impact in terms of the emissions of different species from the fire. And the black carbon is very absorbing and lead to a lot of warming, and so are CO2. And eventually CO will become CO2 in the atmosphere. So in order to estimate how much emissions are coming from fires, it is essential that we can calculate the combustion efficiency of those fires. So let's look a little bit deeper about the fire process here. And you can tell is that smoldering generally occurs near the surface where the oxygen coming down here is pretty, is not is harder near the surface. And the flaming part generally occur above the surface where you have sufficient oxygen supply. So as a result, there are a lot of literature to show that when you have a flaming part, that's where you are able to emit the visible radiation. So by definition, the flaming is associated with the visible radiation. You would not call a fire is in flaming phase until you see there is light in the fire. So certainly this part for light is in shorter wavelengths. The frequency is higher in terms of electromagnetic radiation, where the smoldering of the temperature is lower, and you get a longer wavelength radiation. Anyway, so we want to stick to that concept, the definition, and then take advantage of the new measurements that we can get from space. Is that in 2012, NASA and the NOAA launched the SUMI MPP satellite, and on that satellite there is one channel called day and night band channel. It measures visible light in both day and night from that channel, and you can see at the nighttime they are not only just measuring the city lights, but also able to measure the fire light. So with that concept, we try to use that to quantify the fire combustion efficiency. A couple of concepts here. First of all, there is one variable called fire radiable power. That tells you the total radiable power at all wavelengths due to the fire in a pixel. The fire visible light power is nothing but the fire radiable power in the visible spectrum. And then we define a fraction called the visible energy fraction, which is basically the ratio of these two. By doing so, we're basically saying how much fraction of the radiable power actually goes to the visible spectrum. Therefore, the higher the VEF means more complete combustion, because you have more radiable energy from the fire is due to the flaming, right? So the physics is pretty clear in that regard. So in the past, we have been developing this technique in so the concept relatively are easy to understand, but mechanically, algorithm-wise, and you try to develop end-to-end algorithm and develop product for the community, that takes about almost, I would say, almost 80 years to this point. Okay, so here you some results here, right? So this is the 2017 annual mean of visible energy fraction. And immediately you notice that, oh, here is the Middle East gas flares. Those are our gas flares, that over the ocean, and they are obviously gas flares has much higher temperature, more complete combustion. So in the book part, we are right. The VF is definitely highest over there. And then you can also start to see that the surface type impact, the impact of surface type. So for example, here, right, you can see this part mimics this part pretty well. And certainly Australia, you can see this part very well. So immediately you can see that the land cover has an impact on the combustion efficiency. It is well known from a field campaign that the brush fires will have a higher combustion efficiency than the forest fires. Forest fires are tall, and many of the burning, when they get to the ground, they have a lot of smoldering, not the flaming. But this is the first time we are able to see from space globally. Also give you an idea, this actually work, is that traditionally the community has using FRP, fire relative power a lot. But you can see California fire versus the Australia fire, their FRP distribution are almost similar in terms of how much energy they are generating from the combustion process. But when you look at the VEF, they are very different. This is very understood because in the North America, West North America here, most of them are forest. Where you go to Australia, most of them are savanna or shrubland. And those we know have higher combustion efficiency. So in the larger scale, we are pretty good, and we can verify that with some of the measurements and get a very good correlation there. So another one is that we can also track the life cycle of the fire, right? If you look at this campfire, I don't know how many of you actually know that. I mean, it caused a lot of death and damages, right? What's in the was in NPR for weeks. Anyway, you can clearly see when the fire gets started, they have very highest FRP right here. Okay, they have highest FRP. But in terms of combustion, the most intensive combustion is actually efficiency actually occurred on the third day, on the November 11th, according to our satellite data. Now we try to make sense of that. We looked at there is a weather station about 20 kilometers away from this site, and it shows on the November 11th, the wind speed is actually 7 meters per second, right? And the relative humidity is actually close to about 25% relative humidity. Where compared to the other day, you have slower wind speed and you have a higher relative humidity to 50%. So you can see that's why on the second day, on this day, you got a very high wind speed, very dry air. That makes the combustion much favorable, and you get a higher combustion efficiency. Why is it so? Well, because if you look at the synoptic maps here, you can find, oh, the wind, they're changing the wind direction. Ordinarily, this wind are coming from the north, right, or northwest. But on the November 11th, those winds are coming down from the mountains. So that's called the dipolar winds that drive the things and get them the fire get easily to grow. Anyway, we can make sense by collect all the information we know, and we can calculate, we can make sense of our satellite product. So we can show that by using our product, we are able to better calculate the propagation of the fire lines. This is showing the fire pixel detected by each day. These are the standard NOAA product. This is our product. You can clearly see that we have a better description of the propagation of fire lines compared to the USGS, the aircraft data. But as you know, USGS aircraft data cannot be everywhere globally. So we have this data product now is generated to the community. Another point I want to make is that this VEF has a potential to predict the fire growth. The reason, as I just talked about, right, for the candle, for fires to grow, the wind should be able to push that flaming part to the nearby trees or fields. That's where the fire lines will propagate. Just like a candle, right? If you have a candle, your wind will push that flaming part to the nearbys. Therefore, where you got the flaming will be very indicative if we combine with wind speed and direction to see where the fire will be growing. And that can provide a guidance for the firefighters to put their limited resources at where we should carry the fire. So give you an idea here, last year, you can see here, start from here, the fire gets started, and then on the next day, and then following day. And then you compare this with another traditional product called fire radial power. You immediately see that, right, look at here. These are clearly our fire lines on the second day. And then you can imagine on the third day, they get progressed toward this direction because that's a fire line. Flaming part are mostly located right here, right? On the next day, you can see this get propagated. Where in here, the VF is very low, right? And why is low? Because there is no fuel here. So obviously here is not going to grow next day. Where in here, you see again, the fire, the combustion very high. So it will grow a little bit toward that direction. If you look at FRP, it's a different story. It does not tell you that, the fire line is actually in here. You can see fire line is right here. This FRP is very hot here, but this line, this guy's here, they're just started. In other words, they may have the flaming part that is a condition for fire line to grow. But in terms of total fire size and the temperature, fire size, they are not big enough. So the energy itself is still small, but therefore this VEF gives you more insights about where the fire can predict the movement of fire lines from space. So I want to switch gear to also talk about the vertical distribution of the smoke, because once we have better characterization of the fire energy, flaming, and smoldering, better understanding of their emissions, we also want to know about their how high the smoke layer can go. If the smoke are injected in a very low atmosphere, they can transport to our Midwest areas. But if they are injected very high, then they will be carried by the westerly wind coming to the Midwest. So there are several passive techniques for measuring air-to vertical distribution. So you can have a limb satellite where you launch a satellite, you do not look directly look down to the surface. You just look on a limb. You measure the scattering of the particle, and then you study how much aerosols are in different level. That's called limb. You also can have occultation satellites where you do nothing but directly point to the sun. When the beam of the light from the sun come into the satellite, you measure the extinction when it transfers through the atmosphere, and you can derive the particles or the gas absorptions, and then you get a vertical distribution. Another technique is called a stereo imaging technique. You look the same let's say this is a plume. You look from two angles, right? And then you project the geometry here, and you can, based upon the geometry, you can derive what this height should be. Okay, so those are all good techniques, but this technique does not work very well if the smoke layer is not very thick. If they are not very thick, then you should be able to see the surface feature. Then you cannot do the future matching in order to derive a stereo height. Anyhow, so those techniques all have very limited spatial coverage. What we have been doing is try to develop a technique called using the oxygen absorption spectroscopy. So oxygen, generally in the atmosphere, the vertical distribution is well defined. They do not vary a lot because we know they are considered about 29% of the oxygen in the atmosphere. And the vertical distribution basically follows the exponential profile. The oxygen, however, does absorb radiation. So imagine if you have an aerosol plume, if the oxygen, in the oxygen band, because when the sunlight touches the atmosphere, the oxygen will absorb radiation in certain wavelengths. So if the aerosol plume are higher, then it will have less opportunity for oxygen down below to absorb the radiation. Therefore, the reflected radiation that sunlight sees will be higher. Where if you have aerosol plume is lower, then you give more opportunity for oxygen in here to absorb. Therefore, the reflected radiance back to space will be lower. So in this case, you can look at the oxygen band. What's the ratio between, how does this ratio change? I1 versus I2 change compared to a nearby band where the wavelengths are very close, but the oxygen is not absorbing. Therefore, no matter where the aerosol plume is, you always get the same amount of reflected light. You can take the ratio of the two, and then that's where you can derive the aerosol layer height. So we pick up a band in the oxygen B band. Oxygen B band is at 688 nanometer, where you have chlorophyll air absorptions and the solar reflectance is very low. Therefore, aerosol reflectance is a primary source for satellite signal at this band. So let me show you some results here that my group, Shichen did this work here. So we're able to, for example, retrieve, using this technique to retrieve the aerosol height for different scenarios. This is our product right here. And this is one of a product that generated by the KMI. They are not using the oxygen B band. They are using the oxygen A band, which is around 764 nanometer, where surface reflectance you can see immediately very high because they passed that red edge. So it's not very favorable to retrieve the aerosols. So their product actually is not good as ours. They have significantly low bias, where ours matches with LiDAR data from space pretty well. Another part is that this last year you can see those plumes and dust, and we can all measure them pretty well here. Okay, so this is another kind of a new algorithm that my team has developing, and in that way you can map the aerosol layer height, and now you know, oh, not just 2D but 3D. If the aerosol layer height is very high in the sky, then we should not worry about how they are going to affect the quality of air we breathe. We validated that product with Calypso data, and these are the European product. You can see they're pretty off in that regard. So I want to demonstrate why this is important, right? Why this is important in terms of societal benefits. So air quality forecast is needed by the state and the local communities to make advisories and decisions for mitigating the public exposure to the air pollution. You know, our kids, if they go outside for soccer or for outdoor activities, if they breathe a lot of the smoke, is not good for their health. And so each state has the air quality department, and that provide advisories for them, including Iowa, including Nebraska. And the aerosol layer height is one of the most needed information for those managers, because they want to know if the smoke layer is higher up or actually close to the surface, so they can make very sound advisories for the community. So I give you an example here. On this consecutive 3 days, you can see the smoke plumes are coming to our area. But if you only look at this image, you don't know, should we worry about air quality or not? But this is our retrieval. You can tell that, oh, here, air quality, the aerosol layer height is actually go up to 6 kilometers. We shouldn't worry about that. So a verification can be shown by looking at the EPS data. You can see the EPS measure PM2.5 is very low compared to in the south region that go to 200 microgram per cubic meter, where their aerosol layer height, where the aerosol layer height right here are relatively low. But when you get to our region here, aerosol layer height is pretty high, PM2.5 is very low. Just give you an idea, EPA recommends if the PM2.5 larger than 35 microgram per cubic meter, we will rank the air quality as unhealthy. So it's very normal. In a normal day like today, the air quality is very good. PM2.5 is around 10 microgram per cubic meter. But when we have smoke, we still can get 50. But if the smoke are really close down to the surface, you can go easily to 200. Anyway, and so this one also can help for the prediction, right? Here is a state-of-the-art model predictions made by NASA. You can see they have a wrong prediction on this day because their predicted PM is very high, because in the model, they don't know how much high the smoke go. They don't have the observation data to constrain the model. So most often they put the smoke injection height near the boundary layer. And so when the wind coming carry there, they say, oh, here you got very worse air quality, but this will be a false alarm. But if you apply our product to consume the model, you can get that correction of prediction improved a lot. So finally, I can talk about a little bit about the sensing in the rural communities. This is actually something that a X-Corp proposal. We worked together with David Bennett, with Mark Linderman, and others, and the university in Arkansas, university in Nebraska Lincoln, and the university in Kansas. So the idea here is that we try to put some smart sensors in the Midwest regions to study the climate change, the temperature change. Several motivations here. First of all, is that there is lots number of sensors in the rural communities. The soil data provides land surface temperature, but not 2-meter air temperature. There is a lack of the real-time measurements, especially for the soil moisture and the soil temperature. Just give you an idea, right, in here. In this 4th state, we call Kansas, Arkansas, Nebraska, and Iowa, I call county states, 4 states. By the way, these 4 states actually belong to different climate regions, okay? They never really work together. So anyway, that's also one of the motivation. Now you can see there are 172 weather stations that I put here that provide weather information to the public in real time in less than an hour. But this is only 50% of the whole state's 375 counties. So in this states, we got 375 counties, yet we only have less than half of the weather stations to provide to the community. So there's definitely a need for this real-time information. On top of that, there is a disbelief of global warming is high. So look at this paper here. This is a disbelief, difference from the US averages, right? You have a survey to show what the percentage of a population that believes global warming and what not. And you take that average, and you have each state subject that average. You can clearly see those are hard places. I'm always doing better here, but most of them don't trust them. So we say, well, if we measure these things in real time for 4 years, and we see the temperature actually increasing, will that help or not? So those kind of motivation here. There is also a scientific reasoning for here. So this paper shows the land-atmosphere coupling, that where the land has the biggest impact on the atmosphere circulation. And you can see those are the places I would imagine are inland places, where far away from the ocean, certainly the Midwest areas, Great Plains is one of the hot spots where the land property has very large impact on the air, and that interactions is the highest. And recently there is also a paper to show the soil moisture signature can show up in the global weather balloon soundings. In other words, if we want to have a better prediction of weather, better prediction of climate, we have to deal with the soil moisture and have a better handle of it. And you can imagine that the measuring soil moisture from space is pretty damn hard. And then on top of that, you really don't have too much measurements in the agricultural field to deal with. Even the measure, you don't know they're right or wrong. So there is a clear need for this type of instrument measurements. So through the years, we have developing this sensor called a Smart and Connect low-cost canopy sensor. The reason we call it the canopy sensor is because we try to measure 2-meter air temperature, and pressure, and under the ground, we try to measure the soil moisture and the soil temperature. And we try to do this and measure it in real time so the rural communities can get feel of the data in the fly, and while we're collecting the data. It also helps them to make some decisions about should they irrigate or not, and things like that. Anyhow, we are able to develop some of those sensors, and you can see these two are put in front of a ERF building right there. So in terms of sensor design goals, so we use those different hardware sensor chips to measure the temperature, humidity, and the pressure, and then soil moisture and the soil temperature. So the case is designed here And actually, everything is manufactured in Iowa, by the way, including those ones are manufactured by the local town in the western Iowa. Anyway, so we designed this case. I put those sensors there, and then hook up to the Internet of Things here. Those are the hardware. In terms of firmware, we using LoRa and Wi-Fi, and you transmit the data through the gateway, through the Amazon cloud, and then using the different analysis techniques and the mapping techniques that you can access data right away. We also use the solar panels, and Loranda and Ziyuan, many in my team have developed a lot of, contributed a lot of these things here. So it turns out design something in 24/7 to work in 24/7 in the Midwest is not something easy. We have coldest temperature down to 30 degrees below zero. We have hottest temperature go up to 100 degrees above zero. And you want a sensor that'll work in 24/7 in the midst of snow, in the midst of heavy hails. Is not doing, I mean, take a lot of efforts. But anyway, we learned a couple of lessons that I can share with you. One is that once we implement this, we test everything in Iowa and it worked pretty well. But when we move to the Nebraska, West Nebraska, where on this cornfield right here, we run into problems, right? You can see this actually is a irrigation arm. So when you water is pumping like this, water will get to our case right here. Our case is designed to prevent the rainfall from the sky. We are not designing a case to prevent the rain coming down from the surface, the water coming down from the surface. But in the irrigation field, that's a tough problem. And in order to measure air temperature, you have to let the air to flow, otherwise it's going to heat up. So we still don't have any good solution for that. We try a couple of ideas, and maybe I think we have good ideas so far right now. But for the time being, we come up with ideas that we actually have to put in a case. So we're not going to measure air temperature, but instead just measure soil moisture. And because the air moves, so we assume that air temperature above this canopy is no different from a nearby that there's no irrigation, meaning that in the gap, in some field gaps there, we can put some sensors there to measure air temperature. That's the best now we can do. That's one of the lessons we learned. Another lesson we learned, well, these are some images that you can see here. So we are now able to put there. Another lesson we learned is that we are using solar panels to drive the batteries and such. But when the crop grow, you cannot put this as shorter like this, because if it's short, then crop grows, it blocks the radiation. After a while, you lose the power. So you have to actually go pretty high and have a closed case to prevent things. So there are a lot of very practical side of the things, engineering side of the things that I think it's need to be considered. So nevertheless, I think we made a lot of progress here. So I'm showing here is some of the data analysis. So we put something in the Siemens Center right here. This is the temperature that we measure in the last in the winter time. You can clearly see the temperature and the humidity goes up and down during the fall season last year around this time. So you can see, I can expect in the next 2 weeks, 3 weeks, our season transition will have lower temperature for sure. So how accurate is it, right? So we shipped the sensor to Nebraska. They have a field lab there. So this is our University of Iowa's one. And you got different companies, different universities that develop them. And then you got the most accurate, but also most expensive one, $2,000. Okay, you put them together, and then you look at the data. So here is the data here is the temperature. Here is the temperature that we measured in the fall, actually the winter time a little bit there last year. The Vasella one is a professional one. That's a $2,000 one. And this one is ours. So you can look at the temperature side by side in terms of the air temperature. Clearly that we match well with this red dots right here. There are some other vendors you can clearly see they are a bit off there. That's temperature. In terms of relative humidity, you can clearly see we also track the most accurate ones, most expensive ones very well. But ours is only $150. There is $2,000, and the MS still not real time, and ours are real time. So there is definitely a benefits to deploy this low cost sensors, canopy sensors in large scale. So measuring soil moisture is also challenging, and I learned a lot by talking with different people, in measuring soil moisture. It turns out there is really no standard way to measure soil moisture. And the soil moisture you measure generally have to be calibrated locally. There is no standard protocol to say how you are going to calibrate a soil moisture. The reason is because the soil itself has different properties. And you have to rely on local knowledge. While the data you collect is basically those local sensors, the data you collect is basically electronic signals. So you have to calibrate with locally and convert that signal to the soil moisture. So anyway, this costs $10. You can measure and you can measure the soil temperature. This one costs about $40. You can measure soil moisture in one field. So we are able to calibrate this temperature with our model predictions here. So it's actually not bad, right? This is the temperature, this is the model predictions. Those are the one from the NOAA station, like 10 miles away from here. But anyway, the point here is that the air sensors are pretty ready and they are very good. Soil moisture sensors, we're able to get to work, but any place we want to install it, we have to calibrate with local folks there. So I want to, with that, I want to give you some demonstration so that you can see how we're coming along. So this is the website. Can you see my screen here? I assume you can see it or no?
Yes, we can see it.
Okay, you can see it. That's great. So you can see here. So this is a weather prediction here with a project with David Bennett and Mark. We have a project with ICU. So this is the one of the projects that we try to evaluate our soil moisture in a field site maintained by the USDA in the north of Des Moines. So you can see we are running the model in 3 kilometer resolution and do the predictions. And then on this quadrant right here, the USDA has maintained a very accurate soil moisture that we can evaluate our model forecast. Our plan is then try to put some of our smart sensor right here. I think Mark is leading a project on that. And then if you look at the data access here, here is the environmental monitoring here. That's do things in real time. So showing here is actually temperature measured in my backyard on the deck. I put a sensor on the deck. So this is my measured temperature in the red, and then this is my model forecast temperature in yellow. You can clearly see model has some difference there, but this is kind of experience we want to give to the rural communities, right? They can see things like that and the pressure and the real humidity. And I want to show you something here. This sensor, the robustness of this sensor here has been, so this one has been going on. These are installed in Siemens and has been turnkey free for over a year now. But because we're a smart shop, so we cannot do all the things like a lot of data ourselves and the archive to do that. But anyway, this gives you an idea. We can measure the temperature seamlessly without anybody touch it, just in the terrace right here for over 4 months now. Actually, more than since last winter. I'm not able to show it here because of that. We're not able to the data. It takes a lot of effort to build a database for that. But anyway, we are able to measure that in a year. So my thinking is that, we constantly measure this type of data in somebody's backyard for the 4 years, and we say the temperature is actually changing. If people still don't believe that, then we need to figure it out. But still, somebody, I mean, that's a good area that to explore it. So that's that. And then here is the sensor that we put here, that over the in front of ERF, and you can see the I will measure the soil moisture and the soil temperature in 2 levels right here. So maybe I can go back to here a little bit here. So it's all real time, and you can see we measure soil moisture pretty well. You can even see some impact of the rainfall right here, right? When you have rain, you get temperature, soil temperature gets lower. So this actually made some progress even during the last 2 years of a pandemic here. So, okay, so and we deploy this to Nebraska, of course, anyway. So going forward, I think we have been I have been working together a lot with many of you in the department. We have UI-ICU project and the NSF EPSCoR project, the IDEA project that funded by the EPSCoR program, actually Space Ground program, and we now also have a P3 project, and there are a lot of proposals that we work together. NSF, USDA, and the NASA Citizen Science Project. Mark has been doing some of that. So I really want to carry that kind of collaboration forward. This is something we did in the summer, where Mark has a undergraduate research, REU, and we have a IDEA project. So we will get together and have some group together events like that. So on the horizon, I think we all work for the same university, and we should work together to embrace the funding opportunities that are centered around the climate change, severe weather, and the natural disasters. There is no reason that we should not be working together. We also should think about how to break the disciplinary barriers, especially for those big proposals requires compromise, right? If everybody, as a faculty, we all think that all the things we do, everybody probably have a similar thing, that everything that we do is most important, others are probably not that important. But when these collaborations and the big proposals come together, there need a compromise for that. So do what is best for the students. I think that's probably the punchline here. They will benefit all the work we do and the course we offer. So putting together their interest opportunities first will probably lead us to a long way. So there are courses I hope we can exchange together. There are students, research collaborations we can exchange together. I think that will be the best for the students. The P3 and IDEA are planned out for the next 3 years. I expect there will be a lot of collaborations, and hopefully we now have a regular exchange platform called CASE, Colloquium. I hope we can serve as a platform that we can invite speakers from different disciplines to talk about climate change, to talk about severe weather, to talk about land atmosphere interactions and the societal part of the research. We can also plan ahead to have an interdisciplinary graduate program. If you look around all the Big 10 universities, they all have interdisciplinary program one way or another associated with climate and atmosphere research, not climate research. And so we are thinking to have a interdisciplinary graduate program that everybody can work best for the graduate students. So name can be determined, but that's something that I'm thinking about, and that there are some interests that I heard, and we may work together in this regard. So with that, thanks a lot for your time. I'll be happy to take any questions. Thank you.
Thank you, Jun. Let's do a virtual clap, if you can manage it. Do we have any questions for our speaker?
Thank you. Or clear? Cannot be. My students sometimes give me very poor evaluation for courses.
I guess I have one question about the smart agriculture. I was wondering if there's a education component as part of this.
Oh yeah. The citizen science. There is education. Certainly, when we wrote the proposal, you are not here yet. So we had a table. We have about 20 faculty that, in terms of courses, we're basically using this sensor because this sensor actually switches many things together, from electronic engineering to software to to a lot of things. So we say, well, how can we provide the science and engineering perspective that makes the student have some hands-on activities, looked at weather maps and things like that. So we had 20 faculty from these two institutions offer what course they are teaching, and we actually have a table on that. So the education community is a very strong community on that. So the proposal get pretty good reviews. Everybody likes our idea. All the panelists said they like the idea, but they also said every panel also feel we should have a social scientist on board to study if after 4 years your data actually chooses warming. There are still people don't believe them. Why is it so? And at that time, we had a short notice. The proposal was like written in the holiday. The market knows this. So we are calling like on holidays about it. So we didn't find the right person to do it. And so if you know anyone that specializes in that, we actually originally reserved about 600K for doing that, but we never really had find a person really want to do that. So we still want to give another shot. I expect that the score might come out in the end of the, somewhere around Thanksgiving. There might be an internal selection and then going forward. So I'm still want to pick that up. But if anyone knows that or interested in that, I'll be happy to do that. Yeah.
I have one more technical question about the aerosol height. I love that you can get different smoke heights, but I'm wondering how much clouds present errors into that prediction, or if you're able to separate the difference between clouds and smoke and haze.
That's a very good question. Well, a short answer is that the world is never binary, right? The particles in the atmosphere, you say it's cloud or aerosols, but there are also something in between. It's hard to tell is it cloud or aerosols, called the twilight zones. So anyway, we did the best we can. We use different techniques. One is that the cloud tends to has more spatial variability than aerosols. And the cloud also tends to be, particles are bigger. So you can using the spectra from UV all the way to near IR and look at the spectra. If they are flat, then that's cloud. If they vary a lot and the signal getting lower as continuous longer wavelengths, that will be aerosol. So we use a lot of that technique to differentiate that. Having said that, I can tell you that the atmospheric physicists, there are a whole room of atmospheric physicists try to develop what the air on the cloud. They never find a way to differentiate a clear cut on that. It's just the matter of nature. The boundary is not the best way to do it. So there are some cases we can classify the cloud as aerosol. Sometimes we classify aerosol as a cloud. So there is some noise there. It's definitely it's a challenging problem. Yeah.
Would any of the new satellites that are proposed, such as the carbon mapper or soil biogeography, benefit your analysis? Would that increase predictions, or at this point, what you have is good enough?
Oh yeah, there NOAA is planning the geostationary satellite for 2030. So they call it GeoXO. Now these days there is every acronym need to have X in it. So GeoXO. So that X starts for atmospheric composition. So NOAA originally was all along is trying to track the severe weather or using geostationary satellite. But in the last 10 years, you can see in the US, the severe weather, part of it becomes fire weather, becomes smoke. People are so affected by them, fire affected by them, so they are designing add another satellite will be located in the center of the US. So will be parked in the central US as a geostationary satellite. So they will look at both both the west and the east coast because there's no fires over the ocean anyway, so they don't have to track hurricanes in that way. But anyway, so the techniques will be used for that 2030 satellite sensors. They are going to have the hourly layers or layer height that we may be able to do that. That would be something really cool. Yeah.
Does anyone else have any questions for Jun?
I have a question. I'm really interested in the way you can tell where a fire is burning the hottest and sort of where it's headed. And I just, maybe you mentioned this, but is there right now a way that that information is being fed to the people who are actively fighting the wildfires, or how are they getting this information?
That's good. Good. That's a good question. That the product now, luckily, we got the. So we developed this algorithm, just like anyone else. You develop something and you want to get funded, right, as a faculty. But we tried a couple of times. It was never funded until this year. It's now get funded. So the way we get funded is that we actually build the system almost 50% done to illustrate over the US. And then from there, we actually get a lot of hits these days by looking at just wait a second here. I really want to show this here. Can you do this here? So share the screen with you here again. Maybe I'll show this one here. So we have this one here. So we are able to develop this product, and we got a lot of users from the California. So this is actually for yesterday. And these things, as you would imagine, will be only work at the nighttime where you can see the firelight. Daytime, the firelight will be blurred by the solar light. You can clearly see that those are gas flares in the Texas. Someday you will see gas flares over the North Dakota. Obviously, they are in complete combustion. You can also see fires in the Midwest. In California. And so I got connected a lot, and they are starting to use some of those, hopefully. And then also, I want to share with you is that in here, those are actually not fires. Those are what we call the nighttime waste incineration in the city regions. So where I were to pick those processing facilities that they are relatively hot compared to the surroundings, and they have human activities there. And we discovered that because one of the users in the Montana in the winter time said, "Jun, why your product is showing a lot of fires in Montana in the winter time? We don't have those." So we type in the latitude and longitude of the detection, and we find a Google, and you see this. So we actually have a couple of undergrad students try to verify this product to see these are actually pollutant sources in the urban regions, and then we can use this new data to kind of quantify them in that manner. Yeah.
This is very far outside of my domain, but is there another data set that you could layer in aside from MCE that would help you filter out what is sort of the natural fire versus the flares from fracking or nighttime combustion of landfill waste?
Right. So what we are doing is try to do the certainly you can look at the various two-color images here, but those spots are relatively constant. So we have a student that try to work on a base map so that we can say maybe denote them in a different symbols. Say, well, those are actually not fires; those are human activities. There is actually a group talk about a dirty energy, and they track them using basically community to take pictures. Because some of the state reports dirty energy sources as renewable energy, which is wrong. All right, those trashes you burn them, they are not really renewable energy. So there's a group on that. So we are collaborate with them to see if we can use this data to help them to identify, so that you don't have to each time to rely on manually report them. And so we can shoot a true color image right here, right? This is a yesterday's image, and so yeah, we are working on that. Yeah, I hope if you have students or if there's something you come up with an idea, or you say, hey, this might be some fun, we can work some project together, write a proposal together, I'll be more than happy to contribute. Yeah. Okay.
Well, if there's no other questions, we'll do one final thank you, and everyone can
Thank you.
start their weekend.
Okay, thank you. All right, stay safe. Thanks.
Thank you. Very
See you guys
interesting.
later then. Bye.
Bye.